Okay. Thank you so much for giving me the opportunity to present our research in this workshop. So I will be presenting about the observation of bulk and interfacial spin orbit torques. This work has been partially done at Cornell University and at IIT Bombay. Outline of my, I'm not able to change the slide, sorry. Okay, now the next slide came, right?
Right.
Okay. So outline of my presentation is following. First, I will discuss about the motivation. Then I will talk about the measurement technique, discussing about spin torque ferromagnetic resonance and second harmonic Hall measurement. Then I'll discuss about our work about of interfacial and bulk contribution of field-like torque generated by iridium. And finally, I will discuss about our recent work, which is the observation of orbital Hall effect in niobium ferromagnet and tantalum ferromagnet bilayer. So we know that spin current has many applications, like spin current can create spin transfer torque, and it can be useful for switching, which can be useful for MRAM applications, and it can be useful for spin torque oscillators, and there are various other applications like TMR and GMR based sensors, etc. So one of the very efficient way to generate spin current is spin Hall effect. In this spin Hall effect case, if we pass charge current in a non-magnet, then opposite spins are separated in the transverse direction and we get a spin current perpendicular to charge current and spin polarization direction. Now, if we have a ferromagnet adjacent to the non-magnet, then this spin current can apply torque on the magnet, and that can be useful for switching and spin orbit torque, which are mainly two types of spin orbit torques. One is damping like torque, which is proportional to m cross sigma cross m, and other is field like torque, that is proportional to m cross sigma. So in case of spin Hall effect, this damping like torque efficiency is much more greater than this field like torque efficiency. There is another mechanism to generate the spin current, which is Rashba-Edelstein effect. In this case, if we pass a charge current, then at the interface of non-magnet and ferromagnet, spin accumulation occurs, and which can in turn produce torque on the ferromagnet. And in this case, this field-like torque is greater than the damping-like torque. Now, it is very important to quantify and identify the origin between these two competing mechanisms like the spin Hall effect and interfacial effects. So, the pointer. So by varying the heavy metal thickness, we can do so using the following equation, where we can distinctively separate out the interfacial and bulk contribution, because the interfacial contribution will remain almost constant, whereas the bulk contribution will vary. So next, the other possible way to generate spin current is orbital Hall effect. So in this case, if we pass charge current in a non-magnet, then orbitals with opposite angular momentum is separated out and orbital current is created. Now, this orbital current cannot directly interact with the magnet. So if we have a ferromagnet, then if the ferromagnet has high spin orbit coupling, then the orbital current can interact with the ferromagnet through the spin orbit coupling of the ferromagnet, which can convert this orbital current into spin current. So this has been also predicted and theoretically predicted and experimentally observed in the following papers. And we can also think about similar way like spin Hall effect and Rashba-Edelstein, that at the interface of this non-magnet and ferromagnet, orbital Rashba-Edelstein effect, which has been shown in the following papers. Coming to measurement technique, in case of in-plane second harmonic measurement, we pass a small AC current in a heavy metal ferromagnet bilayer and we sweep the field in the in-plane direction. Now this damping light torque is proportional to the cos phi term, and the coefficient corresponding to cos 2 phi corresponds to the field light term. And it can be originated from O-state field or other spin orbit torque originated sources. So after fitting this with the following equation, we can finally calculate the damping like torque conductivity and field like torque conductivity. And finally, we can obtain the damping like torque efficiency and field like torque efficiency by multiplying it with the resistivity. In case of STFMR, if we pass RF current in heavy metal ferromagnet bilayer, then when resonance condition is met for the ferromagnet for certain frequency and field, then it drives the magnet into resonance, and this anisotropic resistance changes with time. Also the current is time varying, so the homodyne mixture of this current, AC current and AC resistance will create a large DC signal, and we can decompose this STFMR signal looks like this, and we can decompose it into symmetric component and antisymmetric Lorentzian component. Now, the symmetric component in general corresponds to this damping like torque efficiency, and the antisymmetric component corresponds to the field like torque efficiency. So, to quantify the conversion efficiency of charge current to spin current, we calculate this Xi-FMR, and which works pretty well if there is no other sources of field like torque apart from O-state field. But if there are other sources of field like torque apart from O-state field, then we have to use this following formula, where we vary the ferromagnet thickness, and if we feed the data with 1 by Xi-FMR and 1 by ferromagnet thickness, so from the straight line, the intercept will give the damping like efficiency, and slope will give the field like efficiency. So coming to our results, what we did, so we have obtained the STFMR signal, which look like this, and we can see that as we decrease the ferromagnet thickness, we have a large symmetric component, but the sign of antisymmetric component changes, and it is almost kind of negligible for this 3.3 nanometer of oval thickness. So we can see that if we use this formula, we will get a different value of spin torque efficiency. So that's why we have used this formula. And finally, after fitting this with the equation, we obtain this positive value of damping like efficiency and this negative of field like efficiency, which implies it is opposite to the O-state field. And the interesting fact here is that we can see and field like torque efficiency are almost in the same order, which is really surprising. Because earlier the damp efficiency is much greater efficiency. So this is a quite surprising result. So we have further studied this, so we varied the heavy metal thickness and we did second harmonic measurement. So in this case, also, if we see the resistivity of iridium as thickness decreases, we can see the resistivity increases, which implies the interfacial scattering, because of which this increases. And now, if we see the second harmonic signal, we can see for 3.2 nanometer, the sign of this cos phi, cos 2 phi, which is corresponding to field like term, is opposite to the sign of this 1.5 nanometer iridium thickness. So that means we can see as we decrease the thickness, there is a strong dominating effect of field like term, which is basically coming from the interfacial effect. So we did other standard measurements to obtain the damping like and field like spin Hall conductivity from CP and H external, from CA and H external. And finally, we obtain the following curves. So here we have fit the data with this equation. Now we can see that as we decrease the iridium thickness, this damping-like conductivity goes to 0. And it saturates for around spin diffusion length of 1.6 nanometer. And in case of field-like torque, surprisingly, it is not going to 0 as we decrease the iridium thickness. And we have also varied this magnet from COFEB to cobalt, and we obtain similar kind of result. Here also, if we see that for low thickness of iridium, there is a high value of field-like torque conductivity, which is negative. And so we can say that it is independent of the magnet. And finally, we just made a symmetric stack where one side the iridium thickness we've kept fixed, and other side we have varied it from 1.2 to 5 nanometer around. And there we can see that for when both the interface just are symmetric, then it is the field-like component is almost 0 or negligible, we can say. But we can also see here there is a drastic change in this saturation value, so which implies there is cancellation from top side and bottom side. So we can finally have shown the application of this by switching a PMA magnet, and it's standard by applying a symmetry breaking field, the magnet slightly tilts, and finally if we pass the charge current in iridium, then because of the damping like torque, the magnet switches, and we have obtained switching current density of around 10 to the power 11 amp per meter square. Okay, so coming to next part of my talk, which is orbital torques in niobium ferromagnet and tantalum ferromagnet bilayer. So in case of niobium permalloy, if we when we have done this STFMR measurement, we can see there is a small symmetry component and there is a large antisymmetry component, so which gives us the spin torque efficiency, which is negative, because when we compare it with the tantalum permalloy, we obtain similar trend for symmetric and antisymmetric component, and we have obtained this damping like torque efficiency of niobium, which is very small and which is negative, which is also consistent with the theory, because the spin Hall effect in niobium is very small, but it is larger than niobium in case of tantalum. But the surprising fact is that when we have taken nickel as a ferromagnet, in the niobium nickel case, we can see the symmetry component sign just reverses. And so with this thing, and we have also observed similar trend for tantalum also, where the symmetric component sign changes. We have also varied the ferromagnetic thickness to obtain this damping like torque efficiency, which we got positive value. And this sign reversal of the symmetric term cannot be explained by the framework of spin Hall effect. So there comes the orbital Hall effect. So as I explained earlier, that the orbital current generated by niobium is injected in nickel, and due to the spin orbit coupling of nickel, it is converted into spin current, and this orbital Hall conductivity is positive for the niobium and nickel. So among the two competing mechanisms between spin Hall and orbital Hall, when orbital Hall effect dominates over spin Hall effect, we get this positive orbital Hall conductivity. So we have demonstrated the orbital current detection by using nickel as a detector. So I'd like to conclude my talk. So we have shown two important results. One is large interfacial spin torque generated by iridium. This work was entirely done at Cornell University, so I'm very thankful to my group there. And second part, we have shown that observation of orbital Hall torque detected by sign reversal of symmetric component in the STFMR. So this work is entirely done at IIT Bombay under supervision of my guide, Professor Ashwin Tulapurkar. So I'm very grateful to him. Thank you so much for your attention. So I will be happy to take your questions now.
So thank you. So Professor Murli, can please ask the question?
Yes, it's very interesting talk, Sutapa, and it's really nice to see these results. So this, I was wondering, this sign change that you have seen, what is the difference between parmalloy and nickel? Because parmalloy also contains nickel. Why the sign has changed here?
Yeah, so this is very interesting because what happens is that there are two reasons. One is that this orbital current has to enter in the ferromagnet from the non-magnet. So which depends on the orbital overlap between the non-magnet and the ferromagnet, and it is theoretically predicted that this orbital overlap is quite efficient in case of nickel. And another reason is that nickel has high spin orbit coupling. So it can, so as I said, that even if the orbital current is injected in the ferromagnet, though now it has to get converted into spin current, which can be only done if the magnet's SOC is high. So in case of nickel, its spin orbit coupling is very high. That's why this orbital current is converted into spin current in case of nickel, but in case of permalloy, so both these things are, less efficient. So we can see the dominating effect of spin Hall and not the orbital Hall.
Okay, yeah. I think I will let other people to ask.
Okay, so Professor Rohit can ask the question.
Hi, Subta. It's a nice talk. Actually, I have the same question like Professor Murli is asking, because how do you conclude that this is orbital Hall effect? Because the measurement is same, the niobium is same. Like basically, there should be a way or to exactly estimate or to conclude that this is the orbital Hall effect.
Yeah, okay. So I would like to cite some theoretical papers. So here it was in this paper 2008, already it has been shown that orbital Hall conductivity of niobium and tantalum, which is positive, okay. And then in this recent theory paper by the group, so they have shown when nickel is used as a ferromagnet with tantalum, and they have shown with tungsten, then this conversion of orbital current to spin current happens. And since we have taken these metals which has negative spin Hall angle, so we can just conclusively say that since the sign changes, so here it is the orbital Hall effect, because we have also inserted copper between niobium and nickel as a control sample. There also we have obtained the similar trend, same as the niobium nickel case. So it is not generating from any interfacial effect. And also we have made symmetric stack, which is niobium nickel niobium, and there also we don't see any signal, so we can say rule out any self-induced torque. So this sign change cannot be explained by anything else apart from this orbital Hall effect.
So you can also observe the same thing, which if you put the insertion of the copper of 1.5 nanometers, you have the same reversal inside. So it means this interface is not playing any role, right? Because interface, you already break the interface.
Yeah, so I'd like to show this theoretical paper recently. So they have shown by DFT calculation that this orbital Hall conductivity is positive for niobium, so which is also consistent with our data.
Okay. Okay. Can you go to this your previous one more slide? Like there was results on the spin torque STFMR results, right?
Yeah.
Just a quick question. Yeah. Before
for
that.
iridium or for
iridium? Yeah, iridium.
Okay.
So with the thickness dependent, right? With the thickness dependent.
Right. Yeah. This one.
Yeah. So if I see this STFMR spectra for the 1.58 nanometer, 3.3 nanometer, and 2.9 nanometer, I really see the huge difference between the spectra, and with just small change in the thickness. So did you measure the RF power absorption, or like how do you ensure that this spectra is coming from this STFMR only? Like because this symmetric, one has symmetric component, one is a phase reversal of the this anisotropic myotic resistance.
Yeah, okay, so
What
you are
is the-
saying any reflective power, so because of that.
Basically, what is the spin orbit torque symmetry is here? Like, how do you justify this is STFMR, like pure STFMR spectra?
Because yeah, I mean, we have applied around 10 dBm, and so that's how this if we feed this data with symmetric and antisymmetric Lorentzian, so we can quantify from the symmetric part the damping like contribution, and from the antisymmetric part the field like contribution. So using this formula.
No, I understand, but I'm saying that how do you confirm that this the purely symmetric component in the 3.3 nanometer is coming from the spin orbit torque, or is some other contribution?
No, it is.
Mohit, I think he's taking the ratio, na? So even if the power loss is different, the ratio will cancel it out.
So my okay, maybe my point is like if we take the negative spectra, is it the same as the negative field?
Yeah, we have taken the negative field data also. It will just reverse the sign, but if we feed the data, we'll finally get the XIFMR value from this, and we can calculate from XIDL and XIFL fitting this equation.
Yeah. So my point is, Professor Murli, is like because this the sudden change in this the shape symmetry and as well as the almost 100% spin to charge conversion. If you see this, it's not more than 100% because the.
I would okay. Whatever you are saying that 100% conversion is not happening. This is because of the field like torque, which is opposite to the Oersted field. That's why it is looking like 100% efficiency, but we can see it's not very high. So it's not that it's converting 100% charge to spin current. So this field like torque is changing the shape of this STFMR curve.
Okay, so it's also changing in the reverse. That's why I was just looking for the symmetry. If you have the
Yeah.
symmetry of the spin orbit torque, that will be really nice to see. Anyway, thanks. Yeah, thanks for your answers. Yeah.
Okay, so Arnab Bose, if you want to comment, actually, can you speak?
I think it is already commented. So the point is that, we take the ratio. Okay, there are two ways. One is that if we know exactly how much RF current is flowing through the system, then from the symmetry. Hello.
Yeah.
If anyone can calibrate the RF current flowing through the system, then from the symmetry component, we can definitely get the answer. The second way is that we don't need to calibrate the RF current. We can take the ratio between symmetric and antisymmetric component, and in that case, we can quantify. In that case, we don't need to know how much is the loss, but there is a trick. The trick is that the first formula that shows efficiency of FMR that assumes that the RF current that creates the Oersted field. So with that, so it is like self-calibration method. So here clearly we see that if you use that formula, then it clearly fails because figure B gives us a wrong information that the huge charge to spin current conversion efficiency. So what happens is that we have a negative field like torque also acting on it, also acting on this, and that depends on the thickness of the ferromagnet and the non-magnet. So in some case, that negative field like torque can exactly balance the Oersted field, and it will give us only symmetry component. So that's why we need to use the second expression and the developed by Shifang Pai, and with that expression we can quantify this field like and damping like torques.
Okay, yeah. I understood. Yeah, thank you.
Okay, thank you, Arnab, and thank you, Sutapa, for the nice talk.
Yeah.
So let's
Nice talking.